Good morning, everyone. Today we're going to study another approach in the subject that is backtracking. Backtracking is the approach which is used to solve the number of the problem. It's used to solve the sum of subset problem, Hamiltonian, graph cutting, and another problem also. So today we're going to study sum of subset and n-queen problem, how to solve the problem using backtracking. Backtracking is the approach in which we will proceed with the one solution. If we stuck or if we find that the no solution is further and we will find a dead end, we will backtrack to the previous state till the we will find another path. Then we will wait to the another path and will try to resolve the problem. Right? For example, the first problem is sum of subset problem. Now, what the sum of subset problems is that it's a problem in which a set of elements are given to you that are selected, and so from that set of element, there is an integer number given k. The values of that element should be added up to that given number k. So what we are considering that it do not consider do not having any negative values, right? And it is also assumed that the input set is unique. It means no duplicates are present here, right? So in a sum subset problem, there are n positive integers are given. Like if there are given five items, then the five positive weights are associated with the five items. And a positive integer weight W will also be given. So our goal is generally to find the problem like what are the elements whose sum will be added up to that weight W. Right? The backtracking approach we will use for solving the sum of subset problem, and it's an exhaustive approach. We consider that all the subset, irrespective of whether they satisfy the given constraint or not. So we will considering with all the elements, we will draw a state space tree, and we will stop where we will find the dead end, and we will backtrack to the path which is giving us the solution. That's where it's an exhaustive one. We have to explore all the path here, right? And the backtracking can be used to make a systematic consideration for the element to be selected and assume that given a four elements are here. So four elements are having associated with the four weight one to weight four, right? Array W is given here for weight one to weight four. So a tree is diagram that is known as the state space tree. For each and every this problem, whenever a problem is solved by backtracking, we used to draw a state space tree for that because we are trying to explore the each and every path and we have to we are not checking whether they're satisfying the constraint or not. We are searching for each and every path, right? So it's an exhaustive approach, that's why. So let's see how a state space tree looks basically. The tree is given here like the tree is given here like the weight we are starting with the item one, right? Then there is weight one, two, three, four. What would happen if the weight one is included? What would happen if the weight 2 will be included? What would happen if the weight 3 will be included? What would happen if the weight 4 will be included? If we will directly adding to the weight 4, it means we are leaving all the three items. So directly there will be no further leaf node. There will be no further tree. If we are adding the weight 3, it means there is another possibility that we can add the weight 4 also. So there will be a one leaf node behind this C here in this portion. And the first one, if the weight 1 will be added, then I am having weight 2, then I'm having item 3 with the weight 3. Then I'm having item 4 with the weight 4. So I'm having three possibilities further. What would happen if the weight 1 will be added and then weight 2 will be added? What would happen when weight 3 will be added? When weight 4 will be added? This path will show a complete path that what would happen at each and every node when the item will be selected, its associated weight will be added. Right? If all the item will be added, then the final weight will be 16. Now, see here, what would happen if the weight 3 will be added, right? So, after weight 3, if we added only weight 4, it will exclude the weight 3. Now, here, after weight 2, it can added weight 3, then weight 4, item 2 can be excluded here. So, these are the possible conditions which we are trying to mention in a state space tree, like including the item or not including the item, right? So, that's why we're considering it an exhaustive approach. Without checking for the constraint, we are just we are exploring each and every path here. Now see what the problem we are having. The input is given. there's a problem we need to determine such a set is called sum of subset problem, right? So the problem what is given to us that the n value is 5. It means the 5 items are given to us and the total weight the item should be added that should be can be the 21 only, right? So the item 1 is having weight 5, item 2 is having weight 6, item 3 is having weight 10, item 4 is having 11, item 5 is having 16. If you can directly see the solution, then you can check it out like which item we will gonna pick whose sum will be equivalent to my 21. Then my answer will be weight 1, 2, and 3, like 6 plus 5, 11. Then after that, 6 plus 5, it's 11. 11 plus 10, 21. So weight 1, 2, and 3. I can edit weight 1 with weight 5. 16 plus 5 directly gives me the solution, my 21 weight. We can add weight 3 and weight 4. 10 plus 11 is also gain 21. So there are number of paths, number of solutions we are having, right? But when we are solving this with the backtracking, we need to draw a state space tree. And the state space tree says, for example, another problem we are having which we need to solve using backtracking, like 4 item, weight 1, 2, 3, and 4 we are having. Weight 1 with the weight 3, weight 2 with the weight 4, weight 3 is having the weight 5, and item 4 is having the weight 6. Like item 1, 3 weight, item 2, 4 weight, item 3, 5 weight, item 4, 6 weight. And total sum of the subset, the targeted value which we should achieve by adding the sum of these elements, that can be 13. Now, how the state space tree we can generate? See, this is the question which comes in your exam that you need to generate a state space tree for the sum of subset problem. Now, what the state space tree says, the initial node is 0. We will start it with a 0. The very first element is item 1 that is having our weight 3. Now, see here, I weight 3. Now, either the decision is either we can include that item or we can exclude that item. There will be two decisions, right? So the very first decision is the item 1 will be selected. The targeted value initial started with the 0. It means no, we are having no targeted value right now. We have to achieve our sum to the 13. So if I am adding the item 1, it means I am adding its weight. It means 0 plus 3, the outcome will be 3, right? And if no, I am not selecting the item 1, then my weight will remain 0 here. This is a level 1. This is level 0 with the no item. This is level 1, adding item 1, not included item 1. Then level 2. Level 2 says the turn is for item 2. Again, a node is having the two decisions. Either I am including the item or I am excluding the item. If I am including the item 2, yani it means I am adding the value 4. So 3 plus 4, the outcome of the targeted value will be my 7. If I'm excluding, then it will be 3. It will remain the same. Here, the rightmost side, if I'm adding that item 2, then 0 plus 4, my sum will be 4. If I'm not including, then it will be 0. But the level 2 is completed here. Now let's proceed with the item 3. Item 3, weight 5, right? If I'm adding here 5, 7 plus 5, I'm getting 12, right? If I'm not including that item, then my value will be 7. It means I'm mentioning here 0. 0 means not included that item. If I'm including the item, then I'm mentioning that a value or a weight on that edge, right? Then 3. Here I am adding the weight 3, that is having 5. So 3 plus 5, which will be 8. If I'm not including, second possibility, I'm not including. So the total targeted, the sum will remain the same, that is 3. Here 4. So if I'm adding the item 3, then 3 plus 5, the outcome will be 9. So the targeted value I'm mentioning here is 9. If I'm not included, the second possibility, it will remain the same 4. Right. Similar manner, the last branch, I'm putting here a stop. I'm putting here a cross. The cross is mentioning that these are the non-promising nodes because this is the last possibility, including no item at all. So it will always give you the resultant 0. So it is a non-promising node. We will put a cross over here. Now you can also say, okay, why we are putting cross over all these nodes? Why we are putting crossover all these not because our next item is item 4 and item 4 is associated with the weight 6, right? If we are I am adding the 6 here, that I am having my targeted value that is 12 now. So what will be the two possibility? Either I am excluding the item 4 or I am adding the item 4. If I am adding the item 4, then it will be 12 plus 6. That will be 18. That will be exceeded my targeted value. My targeted value is 13 here. So we will put a crossover. It's a non-promising node. Now after here, we will reach to this one 7. If I'm including the item 4, it means I'm adding the weight 6, right? 7 plus 6, it will be 13. It will be equivalent to my target value. We will include it. Second possibility, we will left it, so our weight will remain the 7. Same. And after 8, if we will include this item, then 8 plus 6. Again, it will be exceeded by targeted value. Then 3. If I'm included this 6 plus 3, 9. It is lesser than my targeted value. Somehow, somewhere it is lesser, somewhere it is greater than that. So the non-promising nodes are those for which weights are going to increase than our targeted value. So there is a one solution which will be left. The final solution, if you will see, it is weight 1, 2, and 4. These are the item 1, 2, 4. If we will add them, item weight 1, 3 plus 4, 7 plus 6. It will give us the 7 plus 6, it will give us a weight targeted value that is 13. That is how the sum of subset problem comes. If a sum of subset problem comes, we need to mention the solution in this way in a curly braces, which item we have included and which weights we are adding. And we have to form a straight space tree in this way, and we have to put a cross over the nodes which are non-promising node, and we have to highlight the path which is showing the sum of subset problem. Like I am included my item 1, then I am including my item 2, after that the outcome is 7, right? After that, I am not including my item 3, it is 0 here, see here carefully 0. Then I am including my item 4, that is 6 here. It means 1, 2, and a 4. So the weight 1, 2, and 4 is final solution. We have to highlight this path also so that it can clearly show how using the backtracking approach we have solved this problem, right? Another, all this that I have mentioned that the non-promising nodes we are marked with the cross. You can see here the leaf node in a state space tree that does not contain the solution automatically they are non-promising again. And the leaf containing 7 illustrate that there are the 15 nodes in a prune space tree, whereas the entire is containing the 31, right? Now, the another problem is with the using backtracking approach we solve that is N queen. N queen is generally a puzzle problem. It's a very interesting problem we can say. How why we can say it's an interesting problem? It's just simply solved like Sudoku like. It's a problem. Like there is a chessboard. If a n queen is n by n chessboard, we will have, and we have to place the queen, and in such a way that there are the three conditions, like in such a way that the no two queen can be placed in the same row, same column, or in the same diagonal. Otherwise, the queen will get clashed with another queen. That is the only three important condition which we need to take in consideration, right? And the problem is generally comes with the n queen, like the 4 queen or the 8 queen. If it is the 4 queen, then we have to make a chessboard of 4 by 4, and with the backtracking, we have to show how the problem is that is solved easily, right? So as you can see here, the 4 by 4 chessboard, it means it's a 4 queen problem. Initially, the all the chessboard is blank, so we are putting no queen here, right? And as you can say, it's a backtracking approach to solving using here. It means that we are trying to put the queen in one first row, first column, we will put queen one. Then for the queen two, we will gonna check. Then for the queen three, we will gonna check. If we will stuck, we will backtrack to the queen two. We will relocate it. If we will again if we will again stuck here, or a dead end will become, then we will backtrack to the queen one. We will relocate it again. That is how the backtracking approach work here, right? So it says that okay, since we have to place the four queen q1, q2, q3, q4 on a chessboard such that no two queen attack each other, in such a conditional, each queen must be placed on a different block basically. Now different ith row it should be placed, right? And the condition is each row should be placed at ith. It means the first queen should be placed in the first row. You cannot directly start with the second row. The second queen have to be placed in the second row in any of the column. Means two, either 2 1, 2 2, 2 3, 2 4. It can be placed in any of the J with the 2. It should be restricted here. If we are putting the queen 3, it should be placed in the third row, but in any of the four possible cells we have. Right? So this is the condition we have here. So let's see how the problem get easily solved. This is a solution for the four queen problem, like 3142. Another is 2413 also. Right? So let's see how the backtracking of the solve is to for this queen. Initially, our chessboard is blank, right? So the very first possibility, I can put my queen in one by one. It means first row, first column. One by one means first row, first column, right? So if I'm putting in 1 1, it means that the second queen cannot be placed in 2 1. It cannot be same. I cannot be put it in 2 2 because it come in the diagonal. So the only possible solution for my queen 2, that is the either third cell or the fourth cell. So either the queen 2 can be placed here in the third or in the fourth. Now what would happen? Let's explore further because backtracking is without checking for the constraint, it is solving. If it is found a dead end, then it will start backtracking, right? So if we are trying to resolve for the queen 3, if we are trying to put here queen 3, you will get a stuck here. Now it will come here in the same column. It will come in the diagonal of Q2. It will come in the same column of Q2. Here it come in the back diagonal of Q2. So queen 3 we cannot place. So what to do now? What to do? We need to go back. We need to relocate our queen to another possible solution for queen 2. We can put it in the fourth cell. So let's proceed for the fourth cell. If you will put it here, then the queen 3 can become in my second cell. So we put it here. Now, what would happen if I put it in here? Then my queen 4, I cannot put it anywhere. Now it's a dead end here because it comes in the same column for the Q1 queen. For Q3, it comes in the same column. For this cell, it will gonna come in the diagonal of Q3. This, it will gonna come in the same queen of Q2. So the fourth queen we cannot place anywhere. Now what to do? What to do? We need to relocate our queen 3. But for the queen 3, we are having only one solution. We cannot backtrack. So let's backtrack to queen 2. Queen 2 is having, I am having only two possible solutions. For third cell, I have already, I have reached to dead end. Then only we proceed for the fourth cell. It means we need to backtrack to the initial state. That is the Q1. It means the queen 1 now have to be backtracked and we need to put it into the some other cell. We cannot put it in the one. So let's move to the another. That is the queen 1 relocated to the second cell. In the similar manner, we will put the second queen now. It cannot come here. It will stuck in the column. It will stuck in the diagonal. You cannot put in the straight line. It will come in the column. You cannot put it here. It will the back diagonal. So there are the two diagonal. One is this one is that one. So while checking for the condition, we will put an absolute here, right? So the queen two will be placed in the fourth cell. After solving in such a manner, we will get a solution that for the fourth queen that the queen will be placed in 2, 4, 1, and 3. These are the cell number which I'm talking about, right? As I says you that we are checking for the absolute value. So these are here the absolute value condition like j minus l should be equal to I minus k. That is in the mode basically. The positive we are getting because the diagonal here or the here. The two diagonal condition for we are checking here, right? And it's a solution for our 8 queen problem. Now, a queen problem is generally having, it came in your exam to write the algo also, and we are having two algo. One is place, one is end queen here, and the place algo is generally for searching whether the we are having two algo here, like the place queen or the and queen, right? The place queen is generally for checking that condition which we have seen, like with the mode, whether it's coming in the two diagonal or not. And after it will return true, like the yes, we can put a queen here. Then the end queen will gonna put the queen. So the overall it's include two elbow, like the end queen and the place. And after that the place will return true. The end queen will gonna put that queen in that particular cell. This is how it will gonna work. Let's see here. Let's see the help also. This is a topic we have already covered, right? So this is the algo of place queen. How to place the queen for checking the absolute condition like j minus I, if it should equal to the j minus k. It means that they are coming in the same diagonal. They are crossing each other. It will return false. Otherwise, it will return true. And this is the end queen algo. After calling the place, it will gonna check whether the queen can be righted to the particular cell or not. Only then it will be proceeded. I hope the topic is clear to all of you. Thank you very much.